Hey, it's Mr. Allred, and we've been talking about exponential functions, and now we're going to talk about exponential decay. So here we got a couple practice problems. It says a substance has a half-life of 800 years. Write the function to determine the amount of a 30-gram sample that is left after so many years. Also, how much is left of the 30-gram sample after 3,000 years? Okay. So if we go back to our decay formula, it looks like A of t equals a sub 0 times a little a raised to the t. Okay, so the a sub 0 is the starting amount and the little a was a rate. So what do we have here? It says it has a half-life of 800 years. So that's going to allow us to find this a right here. So that's what we're going to do. Now, we could start with this 30 grams, but we don't really need that in the beginning. So let's just go ahead and put in what we have. So if we set this up with a half-life, that means we're going to end up with half of whatever we started. So instead of using the 30 and 15, we can just use 1.5. Now if we want to use the 30 and the 15, we could divide that out if we want. But then it's to the 800. So this is going to be a pretty fun number. So we have basically 1/2 equals a to the 800, and we're trying to find that a. So oddly enough, we're going to take the 800th root of 1/2. So don't expect anything fancy out of this. We're going to round out the 4 decimal places and hope for the best. So I'm going to take my 1/2 and raise it to the 800th root. So this is going to be rounded off 0.9991 if I use 4 decimal places. Okay. So what I'm going to do is I'm going to write this function with that a now. So I'm going to use a of t equals the 30 grams that I start with times this rate, 0.9991 raised to the t. So that is the function that will let me calculate how much of this substance will be left after t years. The other part of the question is what happens after 3,000 years. So let's work on that. So we want a of 3,000. So 3,000 is our input equals 30 times 0.9991 to the 3,000. So Mr. Calculator is going to be our best friend here. So let's see, 30 times 0.9991 raised to the 3,000. More than I expected. 2.0137, that would be grams. Okay. Alright, so after 800 years it would have been 15. After another 18 years it would have been like 7.5. But we're going 3,000 years. Okay, one more of these. Using exponential decay, a certain drug is absorbed at a rate such that 1/3 of the dosage is left after 8 hours. How much of the dosage is left after a whole day? Okay, so once again, our formula is a of t equals a sub 0, as far as our starting amount, times a, which is our rate, to the t. So things we have here is that after 8 hours, 1/3 is left. So we got to write the function, get the parts that we need. So 1/3 will be left of 1 dosage. So 1 dosage, 1/3 of it will be left in the bloodstream. Now it'll be a to the 8, so our t will be in hours. So we're going to need the 8th root of 1/3, which will be equal to the 8th root of a to the 8th. So we just took both sides of that equation and took the 8th root of it. So let's see what this does give us. So a will be approximately 1/3 raised to the 1/8 exponent, or the 8th root, and I've got here 0.8717 if I use 4 decimal places. So the function that we're writing is a of t equals, and we'll just start it with 1, we don't even have to put that in there, but the rate will be 0.8717 to the t, and a whole day would be how many hours? 24. So we're going to plug 24 into our function. So 0.8717 to the 24, and let's see what that gives us. Mr. Calculator is going to be our friend. So whatever the dosage is, that's what we're going to end up taking, seeing how much we have left. So 2024. It says 0.0305. Excuse me, I left something out there. I left a number out. So let's just rewrite it. 0.0371. So basically, whatever the dosage is that we start with, there's about 3 to 4% of it left in the end. Okay, after a day. All right, thank you.